Warso is turning on the computer. One moment. 1 second.
Oh. So let us start our next lecture, the second lecture by Maryna Viazovska. If you hear us, please tell us something from Warsaw.
We hear you.
Yeah, thank you.
Oh, good.
Yeah, so thank you. And today we continue speaking about sphere packings, and our second lecture is about existence of dense packings. And my plan is to speak about this today and tomorrow. And so when we speak about existence of dense packings, of course, it's first obvious thing is that then we should construct a packing, compute or estimate its density, and this is how we show that dense packings exist. And in particular, this approach works very well in concrete dimensions, for example, in small dimensions. And so in dimensions up to 10 or maybe a bit more, we actually have very good candidates, and we have a lot of confidence that these candidates are indeed the densest packings, even though sometimes, in most of the cases, we cannot prove this. And so there was a very nice paper by Conway and Sloan in 1995, and this paper has a very fun title, which is, I guess it kind of explains itself. So what are all the best packings in low dimensions? And in this paper, they do not prove, or in most of the cases, they do not prove that the constructions they suggest are the best. However, they go into detail of constructions. And here's one method that they suggest for constructing dense packings, and it's kind of very natural one. They call them laminated packings. And the idea is the following. So let's construct packings in higher dimensions from packings in lower dimensions. So suppose that we have some good packing, and then we will take many copies of it and stack it in higher dimensions. And maybe if our building blocks are already dense, then we will find a good way to arrange them, and new higher dimensional construction also will be dense. And so let's see how this works. So of course in dimension 1, we have one best packing, which is just we take our centers of our balls, which are just intervals on the line. We take them, for example, to be integers, and then we cover all our line with intervals. So it's obviously the best packing in dimension 1. And now if we go to try to construct, let's use this packing to construct a laminated packing in dimension 2. And so what we would do, we replace all these intervals by two-dimensional disks. And we try to stack together these lines of disks as densely as we can. And so we would have this first line of disks, and I hope it looks like it's on one line. And now we want to, so this line goes infinitely to the left and to the right. And now we put another line like this on top of it. And of course we can, if you want to do it in the densest possible way, then the new balls should be located like this. And so now we continue same procedure over and over again. And of course, what we get like this, we will get a configuration which we have already seen yesterday. So this would be just the regular triangular lattice or the A2 lattice. Okay, so this idea works in dimension 2. What about dimension 3? So in dimension 3, let's try to do the same construction twice. So first, let's take this densest packing. Okay. And again, so this configuration continues in all the sides. And now we try to put new layer of balls on the top of these balls. So let's imagine that this, yeah. And so now, of course, here we see these holes between the balls, and it would be natural to put new balls into these holes. But now we see if we, for example, put a ball into a hole here, then this hole is too close to it. So if we put one ball somehow as low as we can, then here there will be no more place for it. And so we would have to choose this one. And this one is fine, and this one is again too close, and this one is fine, and this one is fine, and this one is fine. So all our holes are now divided into two classes. And if we are putting the next layer, we actually have a choice. Either we put into these white holes or into black holes. And we see that everything is symmetrical, so it does not matter whether we choose white ones or black ones. The density of total packing would be the same, and so this would be our. And we have this way, actually, because at each layer, we will still have a choice. So this way, we will get not only one new configuration, but we actually get this uncountably many configurations. And with a bit of work, we can see that they are geometrically different. So maybe there is some which still would be somehow similar up to rotation, but this would be some small number of them. And so we would get an uncountably many geometrically distinct packings. Geometrically distinct packings of equal density. And you can, so as an exercise, you can try to compute this density. And so there is actually another approach to the packing that we can do. So probably this, I'm not sure that this falls into a construction considered by Conway and Sloan, but it's still another way to construct a three-dimensional packing from two-dimensional packings. And so this time we can take another packing in two-dimensional space, which we have considered last time. So we can take this square grid on a plane. And we know that the square grid is not as dense as a triangular grid. However, for this stacking construction, actually these layers, they have some advantages. For example, here the holes between balls are bigger and deeper. And also another convenient fact is that now we can actually, if we place a ball here as deep as we can, and we also play here a ball as deep as we can, then they will not intersect, they will only touch each other. And so we will have layers that are not as dense as the layers here, however, they lie closer to each other. And so this will give us a new construction, which is a so-called FCC lattice. And so how this lattice looks like, so it's called FCC, it means face-centered cubical lattice. So if we take a usual cubical lattice, so for example, consider all points with 3 integer coordinates, it will not be a good packing. But now we add more centers of the balls. So we take all the faces of cubes in this cubical lattice and add points at the centers of all the faces. And so we will get a set like this. So it would be 4 shifts of cubical lattice. And so now an exercise that I suggested to first to compute the density of the packings we have constructed here and here. And second is to show that the FCC lattice, actually it can be also obtained from construction 1 if we if we make our choices of holes in a correct way. And so now, maybe last thing I wanted to say, that the theorem of, so maybe a bit of a spoiler is that now the packings we obtained by construction 1 and the packing we obtained by construction 2, they actually have the same density, even though they are different. And this is the optimal density, and this is a difficult and very celebrated theorem by Thomas Hales. So delta 3 is the same as the delta of FCC. So maybe you have some questions. So that somehow we can use this construction and produce this lattice here. So this.
These FCC lattice.
Yes, this. Yes. Okay. So FCC lattice, it's the unique object. It's not a class of objects. Just like this. This is the FCC lattice. So maybe what is not so clear from this definition is that it is indeed a lattice, but yeah, with some work also one can see that this is actually not this is not just a periodic set, but actually a lattice. And so what's about the other dimensions? So in dimensions up to 8, actually we know what is the densest lattice packing in those dimensions. And this is a quite old result from the beginning of 20th centuries. So we somehow know all the densest possible lattice packings. And so here again, so we have in dimension 1, it is just Z lattice or A1. In dimension 2, it is A2. In dimension 3, we have A3, which is the same as D3. In dimension 4, we have a lattice D4. In dimension 5, we have lattice D5, which is the same as E5. Then we have lattice E6, E7, and E8. And so but these are only lattice packings. So of course lattices, this is much more restricted space of configurations. And so now if you want to consider not only lattice packings, but all the packings, so then what is described what was described in a paper of Conway and Sloan, so they, of course, in dimension 1, this is the unique packing, and so in dimension 2, unique up to the technical difficulties that we have discussed yesterday, and in dimension 3, as we have seen today, that we have the lattice packing, but we also have infinitely many other packings. And in dimension 4, this packing is believed to be unique, even though neither optimality of D4 as among all the packings is not proven, and of course also the uniqueness, but the candidate is unique. And in dimensions 3, 6, and 7, situation is in some sense similar to the dimension 3. Here also we have lattice packing, but we also have infinitely many other packings, and they are obtained in a way which is a bit similar to this construction 1, which we have considered here. So we take pieces of, we take lower dimensional lattices, and Conway and Sloan in their paper, they describe combinatorial rules of how to glue them together, how to stack them together, and to create dense packings in dimensions 8, 6, and 7. And in dimension 8, this is the E8 lattice, and it is the unique candidate. And but now this this method of working through, of considering laminated packings seems like it's not all that useful in big dimensions. So it produces beautiful results in small dimensions, but in big dimensions it seems that what we can obtain in this way is not optimal, and something very interesting happens in dimensions 9 and 10. So first, in dimension 9, what Conway have discovered is that we have, again, we have packings which are a bit similar to the situation in dimension 3, when we have lower dimensional packings, stack them together in a certain way and obtain a dense packing. However, he also discovered another family of packings with constant, possibly optimal density, and this time it is a continuous family which depends on a continuous parameter. And so he called it, so he does have what he calls the fibers over E8, so we can take E8, stack them together in a certain way, and obtain dense packings for dimension 9. But also he discovered what he calls a fluid diamond packing. And so this configuration, it works like this. So he fixes a parameter, theta, which is a parameter of this family. It's a number between 0 and 1. And he considers the following. So D9 is theta plus. It's the following set. It's the lattice D9 together with another copy of D9. And it is shifted by this vector, which depends on theta. So it has 8 coordinates 1/2 and 1 coordinate which is 1/2 theta. And it turns out that this packing has, that all these configurations, they actually produce a sphere packing, and these are sphere packings of the same density. And in dimension 10, it's the first dimension where we have a configuration which is not a lattice packing, and it is denser than all known lattice packings. So here there is a configuration which is called Best's packing. And Best is the last name of the person who discovered it. So Best's packing, and it is a non-lattice packing. And here we do not know yet whether it's optimal or not, but this seems to be the most promising candidate. And so maybe now you have some questions. And if no, then I will erase the blackboard and then switch to a slightly different topic. So here I've described what we know about finite low dimensions. But now I will jump to very big dimensions, to dimension D, where D is very big.
We do have a question.
Oh, yes, please.
Yes. Many questions.
Okay.
First.
Yes, so what is actually the reason that the considered approach doesn't work after like 8 dimensions or something?
Sorry?
Why can we use such approach of doing the systems of from lower dimensions only till the 8th dimension?
Why? So the question is why we can use this approach only up to 8 dimensions.
I don't know. That's a mystery. We can use it later. Just the results don't seem to be good. So it's, I mean, the approach, of course, it can be used in any dimension. It's just result seems to be suboptimal.
So, I mean, there is no something special about 8 dimension.
There is something, but I don't know what.
Okay. We have one more question.
Yeah, please.
Yes. Is there any relationship between density and dimension? Something monotone or
not? Okay, maybe I didn't understand exactly the question, but that's what we are trying to understand, right? This is the whole sphere packing problem, is to understand what is the connection between density and dimension. So in very, of course, what we do know that when dimension becomes bigger, the density we can hope for becomes somehow smaller. But and this I will actually speak about a little bit later when I speak about upper bound for the packing density, and then. So the sphere packing constant, of course, it depends on dimension just by its definition, but then understanding what the dependence is, this is exactly the...
We have one more question.
Yeah, I wanted to ask, for this dimension 10, is it known that the optimal packing is non-lattice, or is it still possible that the optimal packing is lattice, but we just... like the best known result so far is non-lattice?
So here everything is conjectural. So the lattice packing problem is solved in dimensions up to 8 and also in dimension 24, but even in dimension 9 it's not solved yet, even though lattice packing problem is a simpler problem, and there is a... Yeah. But it's still, at this point, it seems that it's not feasible computationally to do it, and to my knowledge, same is for dimension 10. So yeah, so we don't know any good candidate which is better than best packing, And in theory, it is possible that there is a lattice which is better, but somehow we have never discovered it before. Yeah, so that would be very strange if this is the case, but yeah, so right now this is only a conjecture. So if you know how to solve the lattice packing problem in dimension 10, please do solve.
Okay, I think we're satisfied.
Yeah. Yes, thank you. So thank you for your questions. So now let's.
And
Oh, there are more questions here. Okay, great. So maybe I start raising.
I have a short question. E is hexagonal lattice, right?
Sorry?
E is a hexagonal lattice, yes.
Oh, okay. So the notation here is a notation which is from the classification of Dynkin diagram. So of course, like it's in dimension 8, so it's not hexagonal, and I did not give the definition. But yeah, so this is a very standard notation in, for example, classification of Lie algebras, and yeah, so there are maybe you have seen sometimes these Dynkin diagrams, and each of these lattices they have their. So this is a root lattice; it has its Dynkin diagram, and from Dynkin diagram you can write down a basis and a gram matrix for the basis. But I do not exactly remember right now how to do it, but yeah.
Yeah, thank you.
One more question.
Hi. So I also have a question about expectations. So do people expect that in large enough dimensions, lattice packings are never optimal?
I would say yes. So I think that most people believe that because there is no reason why lattice packing should be the best among other packings, and just the space of lattice packings is so much smaller than all possible configurations. And probably, maybe in intuitive level, it's clear that in small dimensions, structure gives a lot of advantage, while in the big dimensions, probably those nice algebraic structures, they simply don't exist. There is this phenomenon in algebra that usually when we classify objects, there are like usually finitely many very good objects, and then we just get what we get. So I certainly believe that in very high dimensions, there is no reason why lattice packings should be better than arbitrary packings. And so now, what happens when dimension becomes very big? What do we know here? And so here there is a very, I would say, simple and pretty fact, which allows us to estimate, to give the lower bound on the sphere packing problem, and it tells that a saturated packing saturated sphere packing in dimension D has density at least 2 to the power minus D. And so what a saturated packing means, it means that we have a configuration of spheres which is a sphere packing, and we cannot add any single sphere to this packing. So whatever sphere we will add, it will overlap with one of the spheres we have already selected before. And so here the proof is actually very simple. So suppose that we have a saturated packing, and X would be the set of centers of those spheres. So X with this closed discrete subset, and P of X is a corresponding packing, say with balls of radius 1, and we suppose that it is saturated. And from here we know that the so now let's consider the union of balls with same centers and radius twice bigger. And then if this packing is saturated, it means that these balls, they will cover all the space. Because if there is some point which is not covered by these balls, then we can choose a new center there and add a ball or sphere, and it will not intersect with previous spheres. So this contradicts our assumption. So we see that this is RD. And so now we would see that somehow if the density of this, and now as we compute the ratio of volumes of the ball of radius 1 to the ball of radius 2, so it would be 2 to the minus d. And this essentially finishes our proof. Okay, so so we know that at least 2 minus d is something what we can achieve. And now the question is, can we do better? And so it turns out that what we can do better is depressingly little. And so the next topic I would like to talk about are the probabilistic methods which show the existence of dense packings. And so here we'll actually work with, again, with lattice packings, because even though the lattice packing problem seems to be easier than the general lattice packing problem, but in high dimensions we know so little about both of them. And here actually this extra structure of a lattice seems to be useful, and we will use it in our advantage. And so here's a theorem, which is also a very old theorem, and it goes back to Minkowski. And then the work of Minkowski was somehow refined and rewritten several times in a more modern mathematical language. So here there is a contribution of Hlavka, who was a Czech mathematician who worked at the beginning of 20th century, and then contribution of Ziegel, who wrote this proof in a rather conceptual way, and also an American mathematician, Rogers, who worked in the middle of 20th century and actually contributed quite a lot to this topic, and his contribution goes beyond the theorem that I will state right now, but here I state the most modest version of the theorem. But then the advantage is that we will be able to understand all the details of the proof, and we will have time for most important details in the proof. And so here, this theorem, it's about packing per constant, but for lattice packings. And so it would be the supremum of the packing density for all lattice packings. Okay, so here you see, here the improvement is multiplication by 2. But it's, of course, it's not the only improvement, because even our statement before, it was about any packing, and this one is about lattice packing. So it is a stronger theorem. And maybe one thing I should say, that actually Rogers was able to improve this by then also multiplying this by constant times d. So we have at least a linear improvement in d. And so here the idea of the proof is the following. So let's define the space of random lattices in d-dimensional space, and then somehow estimate or try to understand the packing density of random lattice packing. Or another way, let's show that with a high probability, random lattices are rather good packings. So at least as good as saturated packings. And even a little bit better. So our first step would be, let's construct this space of random lattices. Let's formalize it. So what we would like to consider or rather construct So we consider the space of lattices of covolume in RD. So here, lambda would be a subset of RD. It would be a lattice. And when I write covolume, I mean the volume of the fundamental domain of the Euclidean space modulo all the shifts by the lattice. And we assume that this volume is 1. Or it's equivalent to to compute a Gram matrix of this lattice, and compute its determinant, and if the determinant is 1, then also this volume is 1. And so now, how does this space of lattices, how does it look geometrically? So geometrically, it looks in the following way, denoted by LD. And so, of course, it looks like every lattice, it is we can think of it as a lattice ZD, and then we multiply it by some elements of SLDR. But now, of course, it's true that we can take two different lattices here and still obtain the same, so the two different matrices here and still obtain the same lattice. And when can that happen? That can happen if these two lattices are related to each other by multiplication by a lattice in SLDZ on the right. And so we see that this space, it's actually isomorphic or the same as this space. So this would be the group of all lattices of matrices of size d by d with determinant 1 modulo this subgroup, some such matrices with integer coefficients. So this is the space we are going to study, but we also wanted to speak about probability. And if we want to speak about probability, it means that we have to define a probability measure on this set. And so because this is an algebraic group, there is one very natural way to define such probability. It is to take a Haar measure on this group. And so we can take a Haar measure and then compute the Haar measure of this quotient. And here, what is very convenient for us is that the Haar measure of this quotient turns out to be finite. And therefore, it can be normalized so that it becomes probability measure. Okay, so I will write down what I told you in words. So this is a theorem which probably goes back to Ziegel, but okay, so the group SLDR has a unique left invariant measure mu such that mu of the measure of this quotient is 1. And so, okay, so now we have constructed our probability space. Now how to compute, now we have to find a way to say something about packing properties of a random lattice. And of course there are some, maybe a best way would be let's try to compute the average density, but that seems like a very difficult problem, so I would need to find some indirect way which says us something useful about density and still something what we can compute. And so here is the idea of Minkowski, Hlavka, and Ziegel is the following. So let's fix a ball, some ball with center at 0. And so we are now considering lattice packings of the translates of these balls. And so we consider the following function on our space of lattices. So for each lattice lambda, we will compute the number of points in the intersection of lambda with the ball and without point 0. And so I do not want to count 0 because 0 is a point that will be in all such intersections, and it's somehow not an interesting information, and if we throw it away, our formulas will get a bit simpler. So another way to see this is that we are taking a sum of over all elements of our lattice, and we compute the value of the indicator function of a ball at this point. Okay, yeah. And we are counting over all non-zero points of the lattice. And now, of course, it's clear that this if we take the following lattice packing, which would be the, okay, so before I said that we are considering now sphere packing with balls of a radius twice smaller than the ball here. And so we'll see that this packing, it is a sphere packing. If and only if the function f of lambda is 0. And so now what we would like to do, we would like to compute the expectation of this function on our probability space, and then to prove that there exists a lattice such that the value of a function at this lattice is 0. But so before I will show you how to do this. So I would like to consider one example to look at this space calligraphical LD for d equals 2. So in that case, we can get some taste of what this space looks like. So here's the example. Okay, take the example d equals 2. And so I can write you the answer of what the space looks like. So here we have to consider this. So we define our space to be a space. Our LD is a space like this. But now, if we are interested in packing of disks, and disks are invariant with respect to the rotation group, so we can simplify our life a little bit and also consider here the quotient by the rotations of the plane. And so in this case, this space, it becomes a certain two-dimensional space, a two-dimensional orbifold that I will show you in a moment how that looks like. And so here we will do what is usually done in number theory with this space. So first, it will be convenient for us to think of the Euclidean space R2 as actually identified with complex numbers. So this way we can, if we have a vector with coordinates x, y, then we just map it into this complex number with real part x and imaginary part y. And then orthogonal group becomes reflection, so this becomes complex conjugation and also multiplication by complex numbers with absolute value 1. And so before we considered lattices of volume 1. So, but now it will be convenient for us to take a slightly different normalization. So let lambda be a lattice. And now we think of it as embedded into complex numbers. And now we will introduce the following equivalence relation on the space of lattices. And we would say that two lattices are equivalent if and only if there exists a complex non-zero complex number such that lambda 1 equals alpha times lambda 2. So it means that two lattices are equivalent if they are obtained by each other by either by rotation of the plane or by homothenity. So here we don't fix the volume anymore. And okay. So now let's consider this space. So let H be the upper half plane. So it would be the set of all complex numbers with positive imaginary part. And for each point z at the upper half plane, we can define such a special lattice. So lambda z, it would be the lattice z plus small z times, again, integers. So it's a lattice which is generated by 1 and z, as if you think of them as complex numbers. And so now a useful fact is that every lattice inside of complex numbers is equivalent to lambda z for some z in the upper half plane. So we found a convenient parameter for our lattices. So now so it is isomorphic to some, or equivalent to some lambda z for z in the upper half plane. However, it's still possible that we take two different points z at the upper half plane, and they will produce the same lattice for us. And this can happen for the following reason. It's because, so let's take this lattice lambda z. Okay. Let's first take let's consider a matrix A, B, C, D. It would be a matrix with integer entries and determinant 1, a matrix in SL to Z, and then our lattice lambda z, by definition it is the lattice generated by 1 and z. But then now, of course, we can make a change of basis in this lattice, and it also would be a lattice like this. And so now we can, so C plus, okay, C. Now we can, for example, divide this by A plus BZ. And so we'll see that this is equivalent to a lattice like this. And so it means that if two points at the upper half plane are related by linear fractional transformation for some points A, B, C, D in SLDZ, then they will produce the same lattice for us. And so if you really want to have a space of lattices, what we have to consider the quotient of the upper half space by the action of SLDZ by linear fractional transformations. So now we would see that SLDZ acts on the upper half plane H by linear fractional transformations. Where Z goes to AZ plus B divided by CZ plus D. And so this action, it is a discrete action of a group, and so we have a well-defined fundamental group, and we can choose a fundamental domain of this action to be the following set. So this would be the set that such that, so this would be, I would write down what is a closure of the fundamental domain. And so And it is a set like this. It is this, sometimes it's called a keyhole domain. So we take our upper half plane, H, and here we take this point 0. This is a semicircle of radius 1. And this is a strip between 1/2 and 1/2. And so our domain F is here. And so now these two sides, they are identified by the action of SL to Z. So this side is identified with this side. If we want to have a true fundamental domain, we have to make a choice of which of them to choose. And here's point I, and also like this arc is identified with this arc under the action of SL to Z. And so it means that every point at the upper half plane is equivalent to some point in the fundamental domain. And every 2 points in this correctly chosen fundamental domain, for example, we can choose this arc and don't choose this arc, then every point will have exactly one image inside of the fundamental domain. And this fundamental domain, this is what our space of lattices looks like. Also, if we are somehow, if we don't care about how our lattice is situated inside the plane up to rotations, then this is the right space to consider. If we also care about rotations, we also have to multiply this by all the rotations. And so now what is maybe also one important thing, what is the measure? Because we had the Haar measure. And so here the measure would be the following. So our measure mu would be the measure 3 divided by pi times dx divided by y squared. And here we write z as x plus iy. Here x is the real part of z and y is the imaginary part. So we have such a measure which somehow it becomes thicker near the real line and it fades away at this cusp. And so you see somehow in dimension 2 this space does not look too bad. And somehow bad news is when dimension goes up, then the geometry of the space becomes more and more complicated. And understanding this space, it's also a lot of work for number theorists. And okay, so I think now I ran out of my time today, so probably I will stop today and we will keep the trick till tomorrow. And tomorrow I will tell you how to compute the average of the function we were interested in over this domain.
So let us thank Maryna for your nice talk.